It allows you to effortlessly control your car and provides precision maneuvering for the most advanced military aircraft. But this workhorse of industry is as basic as fluids in motion. Now, engineering's hidden marvel, hydraulics, on Modern Marvels. Our industrialized world depends on hydraulics. But hydraulics is so fundamental to our way of life that we hardly notice it. Hydraulics has taken us from the Model T to the SUV, from Kitty Hawk to the F-22 Raptor. Hydraulics provides the muscles that lift, steer, and drive excavators that mine Earth's precious resources. And is the force behind the machinery that fabricates the very structure of our cities. Hydraulics elevates us, thrills us. It even picks up our garbage.
You look at a lot of applications and we see hydraulics. You think about a car going down the street, of course you have hydraulic power steering, hydraulic brakes. A lot of the roofs on those cars, the convertible tops are all hydraulic controlled. Get into aircraft, all the control surfaces. Amusement parks, a lot of the rides today, there's hydraulic powered roller coasters. Go 0 to 120 in 4 seconds.
Hydraulics is the branch of physics that studies the behavior of liquids at rest or in motion. Liquid in motion is referred to as hydrodynamics. Civil engineers use this form of hydraulics in hydroelectric power plants, manipulating the flow of liquid to push turbines. Those power plants provide electricity to over 1 billion people worldwide. The second type of hydraulics, liquids at rest, is referred to as hydrostatics. Mechanical engineers use this form of hydraulics to produce force through the pressurization of incompressible liquids. If you have 2 pistons within a closed hydraulic system, any force that is applied to piston A will be completely transferred to piston B.
The power of your blow is transferred to the other plunger by hydraulic transfer of power.
One of the benefits of a closed hydraulic system is the ability to multiply force. If piston B has a surface area 10 times that of piston A, piston B will move 1 unit for every 10 units that piston A moves, but at 10 times the force. Therefore, 100 pounds of force applied to piston A will supply enough pressure under piston B to move an object weighing 1,000 pounds. Remarkable in its simplicity, hydraulic multiplication of force is awesome in its capability and is what delivers the brute force for nearly every large machine.
In most people's mind, they consider hydraulics the application of high-pressure fluids, generally speaking, to move large amounts of weight and generate a lot of force. Some of the more impressive applications of hydraulics are just pure, raw hydraulic force. You look at car crushers as an example. It's unbelievable. You'll take 5 or 6 cars piled vertically and they're smashed to just feet. And you have to say, how is that done? It's hydraulics.
One of the most common devices that utilizes hydraulic multiplication of force is the hydraulic jack.
When you push the lever up and down, you're actually pushing on a small piston, which pushes hydraulic fluid, and this fluid flows into a larger piston. Say the small piston that you're pushing has a surface area of 1 square inch, but the large piston that's actually pushing up your car, that might have a surface area of, say, 10 square inches. So for every pound of force you push with that lever, the hydraulic system multiplies that force 10 times.
Unfortunately, in hydraulics, like in everything else, there's no free lunch. So you don't get it for free. In order to get that to work, you have to pump 10 times the amount of fluid.
Although the basic principles behind hydraulics may appear simple, it took many brilliant minds thousands of years to fully understand the inherent power of fluid. The Greeks in 250 BC were one of the earliest societies to look for ways of controlling the flow of water, inventing many hydraulic devices. Some were devised for amusement, like this invention that forced air out of a small bent tube, producing the sound of a bird. Others were more useful, such as the water clock. The Greek who made the most lasting contribution to hydraulics was the mathematician Archimedes, who discovered the first principle of hydrostatics, buoyancy.
His buoyancy experiment was basically based on the concept that a material that is submerged to water experiences a force against gravity, and that force is known as pressure.
He also was the same inventor who said, if you give me a lever long enough and a place to stand, I can move the earth. Fundamentally, that's the principle of levers. And realistically, that's what we're doing with hydraulics on a daily basis.
By 30 BC, the Roman Empire had cast its shadow across the borders of Greece. But instead of destroying Greek society, the Romans learned from it, improving upon several Greek inventions, including the water wheel and the aqueduct.
The Romans, they realized that they had to feed bigger areas, then they had to have a system where they can carry large quantities and at the same time use the concept of gravity.
In the aqueducts, water flowed swiftly, producing as much as 1,300 pounds of pressure per square inch, 25 times the standard water pressure of a city today. Roman engineers often designed the aqueducts to end at cisterns, which would push water up through small openings, turning the liquid into a fountain and providing drinking water for the citizens of Rome. Other aqueducts were sent to water mills, transferring the water's energy into kinetic energy to grind grain into flour. But Roman engineers didn't develop further hydraulic technology, relying instead on the strength of slave labor. In the millennium that followed, the science of hydraulics didn't advance. Old technologies such as water mills flourished during medieval times. Finally, in the 17th century, French mathematician Blaise Pascal made a groundbreaking discovery. By multiplying fluid depth by its inherent weight, Pascal created the formula to determine fluid pressure. This led to the most important aspect of hydrostatics: multiplication of force.
Pascal's principle is the basis for all the work that we do in hydraulics today.
By 1795, Englishman Joseph Bramah had put Pascal's principle to work with his hydraulic press.
When the first hydraulic systems were used around the 1800s, they did use water as the hydraulic fluid, and water does not make a very good hydraulic fluid. Some of the problems it has, it's very thin, so it leaks past your seals. Back in the 1800s, the seals they had were things like leather and ropes and things of that sort, so if they did seal, they didn't seal for very long.
The inefficient hydraulic industry languished, but soon after the Bramah press, a new discovery in America would lead indirectly to a new hydraulic technology. The discovery of gold at Sutter's Mill in 1848 led to one of the largest human migrations in history. Desiring a faster, quicker way to uncover riches, a new method of gold mining quickly spread throughout America, called hydraulicking. And for the next 50 years, hydraulic mining would literally change the landscape of America.
People have recognized for a long time that the power behind water can be enormous. And in the early mining days in the U.S., the gold rush era, we took major advantage of this.
Accessing water sources at much higher elevations, miners constructed wood pipes and attached the ends to nozzles, creating hoses that could shoot water at high velocity against the California hillsides. The hillsides disintegrated, releasing the gold. The scientific principle behind this effective method of gold mining was established by Swiss mathematician Daniel Bernoulli in 1738. Bernoulli found that if a containment of water is forced through a smaller opening, such as a nozzle, the pressure that builds behind the opening would increase the water's velocity, creating a jet. Although it's unlikely that the miners were aware of Bernoulli's principle, their method of mining was effective nonetheless.
The pressures were on the order of 800 pounds per square inch to 1,000 pounds per square inch. So 1,000 pounds per square inch blasting against raw earth. you clean the soil away in a hurry.
Hydraulic nozzles called monitors reached 16 feet in length and could deliver as much as 30,000 gallons of water a minute in a 9-inch stream. At its peak, the hydraulic mining industry in California employed 20,000 people and had returns close to $100 million in gold. The success of hydraulic gold mining was matched only by its devastating effect on the environment. By 1884, it was outlawed in California by a federal injunction. Although hydraulic gold mining had come to an end, a new kind of gold, black gold, was about to bring hydraulics to the forefront of the Industrial Revolution. Daniel Bernoulli's father, Johann Bernoulli, became so jealous after his son published his book, Hydrodynamica, in 1738, that he wrote his own book on hydraulics and predated it in a futile attempt to take credit for his son's findings. Hydraulics will return on Modern Marvels. We now return to hydraulics on Modern Marvels. Until the 19th century, hydraulic power was achieved primarily through harnessing the energy of flowing water. This would change in 1859 with the discovery of oil.
Unfortunately, water has this tendency to turn into solids at something like 32 degrees Fahrenheit. That is, it freezes, turns into ice, and it tends to boil at about 212. So it tends to have a relatively narrow operating window. Oil, on the other hand, can have an operating temperature of well below 0 degrees Fahrenheit to well above 250 degrees Fahrenheit.
The discovery of a suitable hydraulic fluid made the hydraulic press an essential tool on the factory floor and helped to drive the evolution of America's newest obsession, the automobile.
Hydraulics played a crucial part in enabling vehicles to transform from sort of the hay wagon type of things to the ever heavier, ever more comfortable, ever more, livable vehicles that we have today.
By the early 1900s, the automobile industry began to provide a faster means of travel than the horse and carriage. But this posed a difficult problem. How do you make the motorized carriage stop? In 1904, Ransom E. Olds designed the first widely used brake system for the automobile. This external brake consisted of a single flexible stainless steel band wrapped around a drum on the rear axle of the car wheel. When the brake pedal was applied, a cable would contract the band, gripping the drum and stopping the wheel. There was a lot of room for improvement. One of the major flaws of the external brake was that it had no protection from outside elements. Most roads were unpaved, and the metal bands and drums quickly wore down. The external brake was replaced by internal brakes that relied on steel cables and pulleys and the strength of the driver to provide enough force to stop the car.
Strong steel cables provide powerful, unfailing, and flexible connections between the brake pedal and the brake itself.
Of course, as the weight of the vehicles increased and their speed increased, we had to come up with more effective ways to stop these machines.
In 1918, aviation pioneer Malcolm Lockheed began to develop a hydraulic brake system for automobiles. Using petroleum oil as a lubricant, Lockheed designed a hydraulic system that transmitted fluid pressure against the brake drum, allowing for smoother, improved braking ability. In 1920, Lockheed sold his brake patent to Vincent Bendix, founder of the Bendix Corporation. A year later, the Duesenberg became the first passenger car to come equipped with a four-wheel hydraulic brake system.
The way that the early hydraulic systems for braking worked on cars was your pedal would push on a piston in a cylinder full of hydraulic fluid, and that would push the fluid to each wheel. The fluid would come into another cylinder with two little pistons that push out against a couple of shoes, sort of curved shoes that push out onto a cylindrical drum, and when they press on it like that, it creates friction and slows the car down. So suddenly you can transmit a lot of energy to these individual wheel brakes.
Although the brakes were a success, the rest of the automotive industry was slow to adapt.
The American motorist was comfortable with mechanical brakes. You can see, here's a cable, here's the linkage, it's right out where I can see it. And to try and convince this person that you can push fluid through a line, whoa, that was kind of a mind blower. So it was a difficult uphill battle to make that case, and they had to sort of do it by just demonstrating how much more effective it was.
Another hydraulic application that the automotive industry was hoping consumers would soon demand was power steering. But the Great Depression of the 1930s brought its development to a screeching halt. Poverty-stricken Americans didn't have the means or the interest to spend money on the latest automobile gadget to hit the market. By the time the American economy began to reinvigorate itself in the 1940s, another crippling event was to take hold of America.
Most of the R&D efforts for improving hydraulics went into the war effort for tanks and vehicles and ships and things. And so really after World War II was over and people who had been in the war got back into the workplace, that saw a real blossoming of the hydraulic industry.
The automobile industry slipped into high gear. Drivers were ready to go faster than ever before, and Detroit was happy to oblige them.
Those engines were made out of cast iron. They were big and heavy, and they were almost exclusively in the front. They were over the steering wheels. So with all that weight, it became very difficult to turn those wheels.
The technology for power steering had been developed for the automobile before World War II, making it an easy transition for auto manufacturers.
Just take a hydraulic pump and have this driven by the engine, and the combination of the hydraulic flow and pressure is what provided the power to turn the wheels to the left or right. If you turn it to the left, all it does is actuate a valve. The valve opens and routes fluid into a piston which would turn the wheel to the left.
So power steering became an absolute godsend, and the early ones, they wanted to make themselves known, and so your power steering would be totally zero effort. I mean, you could, with your pinky finger, steer these gigantic cars.
Since the advent of power steering and brakes, their hydraulic systems have largely remained the same. Brakes are now complemented with vacuum assist, making it possible to stop even the largest SUV with just a touch from your foot. Power steering also features power assist, which increases the flow of hydraulic fluid based on the speed with which the steering wheel is turned. Modern hydraulic applications for the automobile focus on style and driver comfort.
You can suspend a car with metal springs, but you can also put a piston there with hydraulics to get the same type of springing effect.
The holy grail of suspension is active body control, a feature only found in high-end luxury cars, like the Mercedes-Benz CL Coupe. Active body control will keep the car steady and level, even on the sharpest turns or the bumpiest of roads. The system works by placing a hydraulic plunger on top of the suspension coil. If the car runs over a pothole, within milliseconds, sensors located throughout the car activate the plunger, causing it to extend and balance the car body. But perhaps its most unique feature is the ability to change suspension. Want the feel of a high-end sports car? Just push a button and the hydraulics will make it happen. Although the invention of hydraulic brakes and power steering helped drive the automotive business, the impact these innovations had on the construction industry literally changed the face of the earth. Vincent Bendix, founder of Bendix Brakes, was inspired to develop a better car brake after his father was hit and killed by a car with defective cable brakes. Hydraulics will return on Modern Marvels. We now return to hydraulics on Modern Marvels. The greatest example of the brute strength that hydraulics can deliver is found in the construction industry. Over the years, the excavators, cranes, and trucks that have built our world have grown exponentially in size, achieving unmatched efficiency and power through hydraulics.
If you go to a construction site, you can't help but see hydraulics. It's everywhere. It's in virtually every machine that's on the construction site. And in many cases, or probably most cases, it's because there's just no better way of doing it.
At a warehouse in Youngstown, Ohio, the Robbins Company is putting the final touches on 2 gigantic tunnel boring machines. The drills are nearly 400 feet long and weigh a hefty 800 tons. To move something this massive, there was only one practical alternative.
The amount of force we get from the hydraulics far exceeds what we can get from electrics without going into great cost. Hydraulic gives you more force and power, especially in these type of machines. You need that force to cut the rock as hard as it can be sometimes.
When the drill is activated, 800 gallons of hydraulic fluid travel through 7 miles of hosing to hundreds of hydraulic components. The hydraulic system is capable of pushing the drill's pistons at a force of 5,250 pounds of pressure per square inch.
When we talk about hydraulic pressure, what we're doing is putting force into a cylinder, which in turn puts force against a given component.
Doing the cutting is a 24-foot diameter drill head that runs on 10 450 horsepower motors. The drill head features 46 19-inch teeth that will shatter rock at a rate of 25 feet an hour. Although electrics power the drill head, it's the hydraulics that makes the cutting possible.
Behind me you see some curved items we call a gripper shoe. So if we put 5,000 pounds of pressure on that shoe, that is giving us enough force to hold that machine in place so that it doesn't try to spin in the tunnel.
The grip shoe transmits 4 million pounds of force against a tunnel wall. When the drill is stabilized, a second set of cylinders extend, pushing the drill forward at a force of 3 million pounds.
That shoe weighs about 40,000 pounds, and as it moves very smoothly, as you see, it just shows you how the hydraulics move that kind of weight smoothly and steady.
After inspection, the mammoth drills will be sent to Iceland for the construction of a hydroelectric power plant. Prodigious construction equipment, such as the Robbins tunnel boring machines, represents the unparalleled power that hydraulics can offer. But the history of hydraulics in construction had a fairly modest beginning, starting with the flatbed truck. By 1910, the truck was altered from a simple transportation vehicle to a machine that could carry large bulk materials such as dirt, rock, and coal. Placing these materials into the truck bed was the job of the steam shovel. Unloading them was done with a mechanical dump body.
The construction industry today relies on the hydraulic cylinder. If you consider the dump truck, the early trucks consisted of a winch and pulley system. The operator had to get out of the cab, wind up this crank to dump the bed of the truck. Today, they sit in the cab, they push a button, the hydraulics extends a ram from the cylinder and empties the bed of the truck. The hydraulic cylinder is a method of converting the hydraulic energy to a workable energy in a back and forth motion, and that's really all it does, is it moves in or it moves out.
This is the popular hydraulic type, which operates easily and efficiently under all loads. The end gate is double acting and is operated by a control lever.
The increased efficiency and reliability of the hydraulic dump truck resonated throughout the construction industry. But the impact of the Great Depression and World War II stifled the growth of hydraulic construction machines. After the war, new hydraulic pumps that were designed to increase fluid pressure for tanks and aircraft were introduced to the revitalized construction industry. Coupled with the advent of power steering and hydraulic brakes, manufacturers started to build bigger, heavier, and more powerful machines than ever before.
The construction industry has to move great quantities of earth. So you could have 10 backhoes loading 10 trucks, or you could have one backhoe loading one large truck. And when you did that, you had to move the same amount of earth So that means the piece of equipment had to be much larger.
Today, construction vehicles are some of the largest machines in the world, with nearly all of them utilizing hydraulics, including the Caterpillar 330CL excavator.
The weight of this arm is in the neighborhood of 10,000 pounds. We'd have quite a bit of problem moving that arm efficiently without the use of hydraulics.
Hydraulics also makes it possible to maneuver the Liebherr T282B mining truck and its 400-ton payload capacity. Well, hydraulic cylinders provide the power to lift the bed nearly 50 feet into the air. Cranes rely on hydraulics too. Taylor Machine Works' 80-foot-long and 80-foot-wide gantry crane, called Big Red, uses hydraulics to lift cargo containers that weigh upwards of 90,000 pounds. But hydraulic construction machines don't always focus on strength and power. Timberjack's tree forester uses hydraulics to walk through the forest with the grace of a dancer. But you might want to watch your toes around this ballerina. Whether it's walking, dumping, digging, or drilling, the environment of a construction site is one of the dirtiest places on Earth. Yet, the most identifiable component of the hydraulic machine, the cylinder, never appears to lose its luster.
Any kind of contamination within the hydraulic system is going to have a devastating effect upon the system itself. The cylinders have a wiper on the end of the cylinder head that as the cylinder rod retracts, it cleans off the excess dirt. So when it extends again, it's as though it were new.
But hydraulics has not just revolutionized machines on the ground. It's revolutionized machines in the sky, too. From the latest military planes to the future of commercial air travel. Speedboat racing pioneer Garfield Wood invented the hydraulic lift in 1911 as a means to unload coal from truck beds more efficiently. Hydraulics will return on Modern Marvels. We now return to hydraulics on Modern Marvels. Over the last 100 years, the aerospace industry has transformed from this to this. The astounding leap in aircraft technology would not have been possible without the power of hydraulics.
The airplane really shows a prime example of one of the advantages of hydraulics, to where you can have a single place where you generate your power through the engine and transmit this through hydraulic lines to wherever you need it, whether it's at the back of the plane or in the wings.
Inside the body of a passenger aircraft is an intricate system of pumps and hoses that transfers the highly pressurized fluid that commands nearly every phase of flight control. Most of these systems operate by what is known as fly-by-wire. In a typical fly-by-wire system, flight command is controlled electrically, but powered hydraulically. When a pilot wants to move the rudder, the command is input into a computer. The signal is then sent electrically by wire to the hydraulic system. This system consists of one reservoir per engine that supplies fluid to 2 pumps per engine. The pumps send fluid pressurized at 3,000 pounds per square inch through metal tubing that extends the remaining length of the fuselage, where it connects to an actuator, pushing a piston and moving the rudder. This powerful and efficient system of fluid pressure transference is a huge contrast to the one used by Orville and Wilbur Wright over 100 years ago.
The Wright brothers aircraft had no hydraulics on it. Its basic control was by a lever and cables or pulleys, and this allowed them to have the 3 axes of control.
During World War I, the slow-moving dual-wing airplanes functioned similarly to early Wright brother flyers, relying on the strength of the aviator to move cables and pulleys for flight control.
Those were small aircraft, so therefore it was very easy for the pilot to control the motion of the actuators simply by moving the stick back and forth.
After World War I, the military looked at ways to increase the speed and performance of the airplane. Engineers focused their attention on the landing gear.
All landing gear before were fixed. The Navy decided to do some test in which they actually raised the landing gear through a crank and pulley arrangement, and they found that they could reduce the drag about 30%. But it was very intensive, and therefore hydraulics was looked at as a way of doing this very effectively.
The first hydraulically operated landing gear system was produced in 1929, opening the door for hydraulic applications on aircraft. In the years that followed, planes continued to grow in size and speed, increasing pilot difficulty to command the aircraft using the stick and pulley system.
To be able to move the elevators, for example, or the rudder, or the ailerons. Trying to do it by hand or the conventional pulley and cable system, most of those aircraft would be into the ground or the water.
With the success of hydraulically operated landing gear, military engineers followed the lead set by the automobile industry, installing hydraulic brakes aboard all military aircraft. Soon everything from flaps and rudders to gun turrets and bomb bay doors were utilizing hydraulics to actuate. Although the flight control system still required the pilot to move cables and pulleys, the actuators now moved with hydraulic multiplication of force. But the planes of World War II needed to perform maneuvers faster and swifter than ever before.
The pressures have to increase to be able to allow the pilot to move the surfaces, to do what he wanted to do. You needed a new type of pump.
The gear pumps, which were being used on most military aircraft, were inefficient and would leak at high pressures. Hydraulic pioneer Harry Vickers designed a piston pump, which quickly became the predominant pump for World War II aircraft. With these new piston pumps, fluid pressure increased from 1,000 psi to 3,000 psi. But this increase in pressure also added stress to the hydraulic hoses and sealants.
If a hydraulic fluid would spray onto an engine manifold, it would certainly cause a fire. And many of the fires that you've seen, in general, those were hydraulic leaks that started the fires.
Many times a hydraulic leak would not be something you'd think of with dripping. It's high pressure, so it would leak out of a hose or a fitting. It would often come out as a spray. If there was a fire already started, the leaking oil would feed the fire and you'd have catastrophic events.
To combat this, the military changed to a less flammable kerosene oil called Mil-H 5606. A new sealant was designed as well, known simply as the O-ring.
The O-ring has a unique ability to be able to compress to fill a space, and it's able to do that very efficiently. It's a donut-shaped piece of elastomer, and it became the seal of choice for most of the products that are in a hydraulic system.
By the end of World War II, innovations in aeronautic hydraulics found an easy transition into the burgeoning commercial aircraft industry.
Commercial airlines discovered that they could also take advantage of the hydraulics to where their aircraft could be made larger, lighter, and able to hold more people. So by having these aircraft that could carry more people, it made airline travel more practical.
The Mil-H kerosene-based fluids used in military aircraft were deemed unsafe by the FAA. In 1948, aircraft manufacturers addressed this concern with the development of Skydrol 7000.
This fluid was a phosphate ester and is still in use today. Phosphate esters are a class of synthetic hydraulic fluids which have very good lubricating qualities. In addition, they tend to be fire resistant.
Except for the fluid, the hydraulic functions of early commercial aircraft were almost identical to those used on military planes. Hydraulics actuated the landing gear, moved flaps and rudders, and controlled the brakes. Because of the size and weight of commercial airliners, hydraulic pressure increased to 3,000 psi, the same pressure already used on most military aircraft. and construction machines. Although this increase in fluid pressure gave pilots the muscle to operate actuators through cables and pulleys, by the 1980s, it was time for a change.
The problem with the cable and pulley is, as surfaces become larger and larger, it is very difficult even to give it a correct feel. Electronics can make this decision much quicker. Today's aircraft have much greater performance capabilities and have to do things like moving these surfaces almost instantaneously.
Fly-by-wire hydraulic systems continue to dominate the flight control of even the most advanced commercial and military aircraft.
The hydraulics aboard the F-22 fighter plane are pretty much state-of-the-art. You have all of the primary flight controls, the landing gear, the weapons bay doors open very quickly and close very quickly to launch missiles. The propulsion system depends very heavily on hydraulics in the F-22 for control of the inlets and the exhaust nozzles.
The biggest advancement in hydraulic technology for aircraft is the development of the EHA, or Electric Hydrostatic Actuator. Originally developed in the early 90s, the EHA contains all the components of a hydraulic system in one small package. By placing EHAs next to aircraft control surfaces, designers eliminate thousands of feet of hydraulic tubing and hundreds of pounds of weight.
This EHA is considered cutting-edge technology because it removes the distribution elements that are part of a conventional hydraulic system. There are two electric motors that work in tandem. We also have hydraulic reservoirs to capture the thermal expansion and contraction required to power the hydraulic pumps of this system. The linkage here is attached directly to the flight control surface.
The first aircraft to use EHA technology for primary flight control will be the F-35 Joint Strike Fighter. The first commercial aircraft to feature EHAs, in this case for secondary flight control, will be the new Airbus A380. Boasting a length of 239 feet and a wingspan nearly as long as a football field, this is the largest commercial airplane ever to be built. New hydraulic technology had to be created to control an aircraft that weighs well over 300 tons.
Certainly, the A380 offered the hydraulic system designer several major challenges. If we were going to use the conventional hydraulic system concepts, 3,000 psi, for example, the pumps would be massive, the lines, fittings, and hoses would be massive. A solution to this was to increase the pressure, not from 3,000 to 4,000, but to take it to the next step, 5,000 psi.
But as the aerospace industry continues to look for ways to improve upon the efficiency and safety of flight control systems, engineers are investigating the idea of using electric motors to actuate control surfaces, thus eliminating hydraulics completely from flight control. Before that happens, a formidable hurdle lies ahead. Engineers need to develop a practical motor that can create the needed force to actuate the surface controls efficiently. But hydraulics not only shapes our future, it brings the past to life. Prehistoric dinosaurs animate with the help of hydraulics. The Airbus A380 will feature 4 independent primary flight control systems. Each of these systems is capable of operating the aircraft should the others fail, creating a redundancy system unequaled by any military or commercial plane. Hydraulics will return on Modern Marvels. We now return to hydraulics on Modern Marvels. Hydraulics not only plays a key role in our work lives, it plays a role in our play lives too. Universal Studios in Hollywood, California is home to some of the most cutting-edge hydraulic attractions in the world.
You would not be able to have any of these attractions move this much weight and be this reliable without hydraulics. It just would never happen.
One of the more complex hydraulic attractions at Universal Studios is Earthquake the Ride. Passengers entering this stage are given an idea of what it's like to endure a massive seismic event. hydraulic system for earthquake runs on just two 50-horsepower motors. The system works by sending fluid through hydraulic pumps to a series of accumulators that store the fluid at pressure, keeping it ready for each show. Underneath the floor of earthquake, a dark cavern is home to dozens of hydraulic cylinders. Moving the 20,000-pound floor bed in linear and lateral movements, the cylinders create the feeling of an 8.3 Temblor. But that's only one of the hydraulic effects on this ride.
As the show's going on, we have a large slab that'll fall. It's got 4 big hydraulic cylinders behind it. It is probably somewhere around 9,000 pounds. And also we have a train that comes out and crashes right in front of the tram. It's driven out by a hydraulic ram.
When the tram exits the stage, the hydraulic cylinders retract, carefully putting all the props back to their original positions.
You have to keep the show exactly the same every single time. Earthquakes, hydraulics are very sophisticated.
Universal's Terminator 2 3D also features several precision hydraulic effects. Hydraulics control the platforms that raise and lower different characters onto the stage. And they also animate the 6 gun-toting Cyberdyne robots, using 3,000 PSI pumps to actuate cylinders in the head, torso, and arms. But the attraction that utilizes the most hydraulic effects at Universal is Jurassic Park, the ride. Visitors cruise through prehistoric tropics, encountering a bevy of life-size and lifelike dinosaurs, including a 40-foot-tall Ultrasaur that uses 15 hydraulic cylinders in the neck alone.
This particular figure we just saw, the oil that comes in here, this is a pressure line. It's set at 3,000 PSI. The hydraulic module here will distribute the oil to the figure itself, which has, the one we saw is just the torso and head. It has 6 separate moves, 6 separate cylinders, and it's all powered by hydraulics.
After encountering several dinosaurs, the ride drops another hydraulic thrill, so to speak.
We use hydraulics on the following car for 2 reasons, really. It's more controllable than any other kind of power, and it's also less expensive energy-wise. The cylinder is actually hooked up to a block and tackle. And what that does is that increases the motion of the Jeep compared to the cylinder. The Jeep will move 32 feet, while a cylinder will only move 9. So all we need is a 9-foot cylinder to get that much movement. That increases the force on the cylinder, but the hydraulics overcomes that, and it's no problem at all.
Then there's Waterworld, which uses a hydraulic catapult to launch a 2,000-pound airplane 60 feet across a man-made lake. And of course, there's old Bruce the Shark. With so many hydraulic attractions, it's no surprise that even the trams at Universal run with the help of hydraulics. Whether it's entertainment or construction, when something big needs to be moved, hydraulics still remains the power of choice, at least for now. But the continuing advancement of electronic systems may eventually lead to electric motors replacing hydraulics as the power source leader in force applications.
I believe the future of hydraulics is a combination of electronics and hydraulics. In some applications, hydraulics may be phased out, but we will never see the power density from the electronic systems that we see from the hydraulic system.
Just can't fathom any other technology that will be able to generate hundreds of thousands of foot-pounds of torque or the thousands of tons of force needed to drill a hole in through a mountain or under a lake.
Whether or not hydraulics is supplanted by another power application is yet to be decided. But until that day comes, when something big has to be moved, when a high amount of power is needed, with precision control, hydraulics will remain the power of choice.
This great empire was also one of the most complex, fueled by the fervor of Islamic holy warriors, yet a modern